All right, now we're starting. Alrighty. So we're actually going to continue with section 1.1. It's actually a pretty long section. How's the quiz? Okay. All right, so we're going to continue. So be warned, the rest of chapter 1, or pretty much everything else I'm going to do in chapter 1, I'm just going to go through it. I'm going to throw all this information at you. We're just going to keep going. It's just going to non-stop. It might seem like a blur. But most of the time, it's all review. Technically, it's stuff you should know, so I'm not really teaching you. I'm kind of reminding you what you should know. So that's sort of the idea we're going through. There's a lot of algebra that I'm going to need you guys to remember, so we're going to go through and we're just going to get through it, how to evaluate functions, find domains, that sort of thing. Introduce different kinds of functions, so we're going to go over exponential functions and log functions in case you guys forgot that, and all that sort of stuff. But last time we ended with a word problem where we kind of went from the words to algebra and we solved it. So now we're really going to go and focus back on the algebra, how to simplify something, how to plug things into functions, that sort of thing. So we're going to continue with evaluation of functions. Or function evaluation, whatever you may have called it. This is basically computing the outputs of functions. For given inputs. So you know what the input is, you want to find the output, basically. Might sound complicated, but it's not. So now, when I show you the example, you're going to realize, oh, that's what it's not a big deal. So let's say you're given a function x squared plus 1. And I ask you to evaluate some things. Find f of 1, f of 2, f of 5, f of a, f of a squared, f of minus a, and f of a plus h. Okay, so I gave you a function. The definition is f of x equals x squared plus 1. And I actually want you to find the value of the function at these points. Okay, let's go through these quickly. What's f of 1? How do you get 2?
Just put it in the
Right.
equation.
Everywhere I see an x, I will put a 1. So this is 1 squared plus 1. Which gives you 2. Practice writing it like that. F of 2, similarly, 2 squared plus 1, that would give you 5. By 2, f of 5. 5 squared plus 1, that would give you 6. F of a, that's just a squared plus 1, which I would leave as a squared plus 1. Get in the habit of putting things in parentheses, though, that you're plugging in. I'll explain why pretty soon, because I saw some mistakes on the quiz. A squared means you open brackets. Wherever I saw an x, I now put in a squared and plus 1. So this basically becomes a to the 4th plus 1. And f of minus a, that means I open brackets, I put in a minus a. Basically gives me a squared plus 1. If I have f of a plus h, it means I open brackets where the x was, and I plug in a plus h. So that would give me a squared plus 2ah plus h squared plus 1. Questions so far? You're okay? The idea behind all this, f of x can be thought of a template. So when you're given a function definition in algebraic form, right? Remember there are many ways we can represent a function. In algebraic form, you can think of that as being a template. So when they say f of x equals x squared plus 1, the idea is they're telling you what the definition is. F of whatever is here is just going to be whatever squared plus 1. Right? That's sort of the idea. Wherever that x is, you think of it as a placeholder. It's just a template that you're going to be plugging things into. Right? So, for example, on the quiz I was walking around, seeing what some of you guys are writing, and I noticed for one of the problems, we're actually going to do some of these later. But there was a problem where I asked you to find. So this wasn't an original example. This wasn't a planned example. Let me just talk about it since we're here. So in quiz 2, problem 5, I gave you a function, x squared minus x plus 1. And I asked you to find and simplify f of x plus h minus f of x over h, called the difference quotient, a very important expression. I was walking around and I noticed that a lot of people got the answer 1 here. The answer shouldn't be 1, it's not 1. And the reason why you would have gotten 1 is because you didn't understand this idea. So I know what happened was you guys probably went here and you saw, oh, f of x plus h. So I have x squared minus x plus 1 plus h. And then you do like minus, and then you're going to have this. The thing is when you do that, this here is just f of x by itself. The plus h is separate. So you're always going to have this killing that, and then you have h over h, which gives you 1, which is the wrong way to do it. Right? The right way would be the x is going to be replaced by x plus h, and this x is going to be replaced by x plus h. The thing is, if you do it that way, what you're actually finding is f of x plus h minus f of x, which is, they're not the same. There's a difference between adding an h separately and actually plugging in x plus h. What you should have looked like was x plus h squared minus x plus h plus 1. Then you minus open parentheses, put that guy in here. And you would have continued from there. Right? So the answer should not have been 1. I saw several people write 1 is the answer. This is where the mistake happened. You evaluated the function incorrectly. Right? You want to think of functions as templates. The x you think of just as a placeholder. Whatever you put in brackets here, it replaces all the x's in that definition. So I'm not going to continue here because I have more examples like this. So we will do some examples like this. I just wanted to keep that dog as we walk by. So those are function evaluations. Basically, the idea is evaluating a function at a certain point. How you do that? Think of x's as placeholders. Whatever goes in brackets here, you put it where the x is. So for example here, it doesn't matter what I write. I could write f of smiley face. What you're going to do is write smiley face squared plus 1. Doesn't matter what's inside the brackets. Doesn't matter what it looks like. It's still a chair kind of thing. Doesn't matter how ugly it looks or whatever it looks like. As long as the thing here is in the domain, replace all the x's with it. So some of you might have forgotten how to do that, so that's why I reminded you. Slightly more complicated example, not much. 3x squared plus 2x plus 1. Find h of 0, h of minus 1, h of minus x, h of x plus. So for this, h of 0 is
1.
it's 1. Everywhere you see an x, you're going to put a 0. That gives you 1. Similarly, h of minus 1, everywhere you see the x, you're going to put a minus 1. What does that give you?
2.
Right, so you're going to, minus 1 squared is 1, PEMDAS, right? So we're going to do the square before we multiply. So 1 minus 1 squared is 1 times 3, that gives me 3, minus 2 is 1 plus 1, so that gives me 2. So that's h of minus 1. If I have h of minus x, this is 3 times minus x squared plus 2 times minus x plus 1. If I could simplify, minus x squared is the same as x squared. 2 times minus x is minus 2x plus 1. So h of minus x just changes the middle sign. How about h of x plus k? How's that going to look?
3 times parentheses h plus k squared.
X plus k squared.
Plus 2 times x plus k.
In parentheses,
Plus
x plus
1.
k plus 1 is separate.
And then you have to span x plus k squared.
This becomes
X
x
squared
squared
plus
plus
2xk plus k squared plus 2x
so this becomes 3x squared plus 6xk. Can you combine any like terms there? No. That's not. Okay. Questions? Okay. Let's talk about the difference quotient. This is what you had on the quiz. Be reminded of what it is, given a function. By the way, you have to remember this, right? So in a quiz or a test, I might not give you what the definition is. I might just say, compute the difference quotient, and I expect you to remember the formula. That's the difference quotient. Given a function f of x, its difference quotient is either of the expressions so it's either going to be this one, f of x plus h minus f of x over h, or we can write it as f of b minus f of a over b minus a. By the way, this is equivalent to the average value, average rate of change, which I also asked you as a bonus in the quiz. So you could have written down either one of these formulas. I believe that actually with a and b, so this would be the answer to that bonus one. Right? This expression is called the difference quotient. You would have seen it in algebra and pre-calc a lot by now. Probably don't know why we asked you to compute that. In chapter 2, you'll see why we asked you to compute that. It's actually a formula with meaning. The spoiler would be it's actually a slope formula. Kind of like y2 minus y1 over x2 minus x1, but actually that's pretty much exactly what it is, but we'll put it in context and say why we care about it and what we're going to use it for when we get to chapter 2. But it's a very important formula. It's called the difference quotient. So if I say compute the difference quotient, I'm asking you to do one of these two evaluations. And if I don't specify, you can choose either one, and it'll be fine. So let's do some examples. Suppose I tell you that f of x is 2x plus 3. of x is 2 plus x minus x squared. K of x is equal to x over x plus 2. Find a f of b minus f of a over b minus a. G of x plus h minus g of x over h. C k of x plus h minus k of x over h. Actually, I didn't use an x here, I used an a, but it's actually the same idea. So I basically gave you 3 functions and I want you to compute the difference quotients for each of them. And being able to compute one of these is very important. It will actually be on the first 2 tests. So on test 1, there's going to be a problem where you have to do this. And on test 2, there's going to be a problem where you have to do this. So pay attention to this. Right? It's a very important. Difference quotient is a very important topic. It's going to be on 2 tests and the final. Guaranteed. Okay. Let's do part A. So if I had f of b minus f of a over b minus a, what would that be equal to here?
2b plus 3 minus 2a plus 3
Is that okay?
over, I don't know.
Over what? b minus a. That's
b minus a?
So this is your f of b, that's your f of a, all over b minus a. Is that fine?
No,
What's wrong?
because you have a negative in between those, so you have to close parentheses and change the sign and
Parentheses.
cancel the 3 out.
Yeah, that's fine. So now we're going to simplify. We expand the brackets. The parentheses. Yes, the 3's will cancel in this case. And I would have 2b minus 2a. Can we do anything there?
Wait, factor out the 2 on the top.
2 is a common term. You can factor out the 2 from the top. So this is equal to 2 times b minus a over b minus a. That would cancel, and the answer is 2. We will get back to this, but notice that this is a linear function, and when I plug it into the difference quotient, the answer is actually the slope of the straight line. That is not a coincidence. Anytime I give you a straight line, ask you to compute the difference quotient, after you go through everything, you should end up with this guy. It doesn't work for all functions, but for straight lines, it has to be that number. That's one thing you want to remember. I'll re-emphasize that in chapter 2, so probably don't want to not to kill yourself remembering that now. One other thing that it's important to remember here is in 205 especially, some functions can be really ugly, but in 205 it's always going to be the case that you're not done simplifying until you cancel the original denominator. So when you're simplifying the difference quotient for any of these, at some point you're going to have to cancel that b minus a, or you're going to have to cancel that h. You have to be able to cancel the denominator. When we get to chapter 2, the real reason is going to be, is because we're going to want to plug in a number that makes that denominator 0. We can't divide by 0, so we have to keep going until we actually cancel it, so that we can plug in that number. So the idea is, for example, is if I ask you to compute this and you got to here, you're going, oh, yeah, I'm done. No, you're not done. You're not done until that b minus a is gone, right? So in case, I know students always then ask, how do I know when I'm done? When do I keep going? Well, for this, you keep going until that denominator gets canceled. The problem is not complete until the denominator is canceled, right? For difference quotients, you have to cancel the denominator. So b was g of x plus h minus g of x h. Here, remember my g of x was 2 plus x minus x squared. What would that look like here? G of x plus h looks like what?
2 plus x plus h minus x plus h squared over h. Oh, no, minus.
That's this part. That's
minus,
your g of x plus h
yeah,
minus.
minus 2 plus x minus x squared over h.
We're forgetting something?
Bracket.
Parentheses around this. Don't forget the parentheses. Once you open a negative sign, open parentheses. Okay, now what? Don't forget it. Now what? What can I do here? Nothing. I can just remove the brackets basically. This?
It's time
What do I
x
get?
squared plus 2xh plus h squared.
And this also stays in parentheses. That negative sign has to be distributed. At this point, I can expand the parentheses here.
Yeah.
That's all over h. So basically, this is 2 plus x plus h. Expand the brackets here. You get minus x squared minus 2xh minus h squared. Minus 2 minus x plus x squared over h. Now what? Combine like terms, so 2 would kill the 2, x will kill the x squares, minus and plus I as well. What do we have left? H minus 2xh minus h squared all over h. Factor out the h. Remember, we're not done until that h dies. So we can factor an h from the top, it's a common term. 1 minus 2x minus h over h. There's multiplication, which means I can cancel across it. So my final answer is that expression. I think my k of x was x over x plus 2, was it? All right, so what does this expression look like? Minus? Okay. How do we simplify that?
Can you multiply this equation by h? Like add h to both, that way you can subtract.
Add h to where?
Make the denominators of like, we just
Okay.
subtract,
How would you do that?
add h to it.
Add h to the denominators?
Yeah. No, to this fraction, add h. I would add it.
You can't add
No,
h.
you have to multiply the entire denominator.
Yeah, you can multiply and divide by this denominator, multiply and divide by that denominator, etc. If you only had two fractions, that would be the way to go. It's actually quicker in this case to multiply by the LCD over itself. This is what's called a complex fraction. It means you have a fraction that has fractions inside the fraction. The quickest way to kill one of those is to multiply by the LCD over itself, which is the least common denominator. In this case, that is going to just be the product of these two denominators. So I'm going to multiply by a plus 2 times a plus h plus 2. And I divide by it so that I can multiply by 1 and not actually changing the value. This guy here is called the LCD, least common denominator. It's the product of all factors in the denominator. So you look at all the denominators in all the fractions. This, and that. You need the product of each factor raised to the highest power that they appear. You get this. And now you multiply out. Now what happens is when you take this guy and you multiply this fraction, what's going to happen? This a plus 2 is going to cancel that, right? And you only have a plus 2 left over. So here we're going to have a plus h times a plus 2 minus, when I take this times that, the a plus 2's cancel, and I'm left with this. So I'm going to have a times a plus h plus 2 all over h times that. So now I'm not a complex fraction anymore, right? And it's quicker than multiplying top and bottom here, combining the top, then you have to do a flip and multiply. You take 2 steps, a lot of room for errors just to get to the same point. So the quickest way to kill a complex fraction is to multiply and divide by the LCD. That's a trick that you should remember. It'll come useful, I promise. Another thing at this point to remember, do not expand the denominator. Whenever you're trying to simplify a fraction or a rational function, as this is called, you never want to expand the denominator. Best way to simplify is to factor things and cancel them, right? So that's one of the things you should remember. So here, I'm not going to multiply this out. I might want to multiply out the numerator though, in case I can get any common terms to kill each other. Because remember, the goal is cancel that h. And right now I do not have a factor of h in the top. So I have to do whatever I need to get a factor of h. At this point, there's nothing much to do except just expand it. You get questions like that in your first quiz. So how do you expand that? What do you get? A squared plus 2a plus ah plus 2h minus ah minus 2 all over h times a plus 2 times a plus h plus 2. And now the a squares die, the 2a will die, the ah will die. And so on the top, the only guy I have left is 2h. I'll write down the exercise. Now in the top and bottom, I have multiplications only, so it means I can cancel. So my final answer is going to be 2 over a plus 2 times a plus h plus 2. Questions? Learned some valuable lessons here. We're simplifying complex fractions by multiplying top and bottom by the LCD. Gets you done quickly. When you have something like this you want to simplify, you never expand the denominator. expand the numerator if you have to. The point would be to factor it so that something might cancel. Right? So that's what we did here. And it turns out that it ended up in a nice factored form where something canceled. Not something, the original denominator. You have to cancel that h. That's it for function evaluations. Right now we're going to talk about piecewise functions. Functions use definitions depend on where we're evaluating. Here's the notation. For example, f of x, you have this squiggly bracket, they write it like that, and they write out the definitions and where they want them to take effect. So I can define this function to be 1 when x is between 0 and 1, and I can define it to be something else somewhere else. Because when you're modeling a real-world problem, the definition might not take on the same kind of thing at all times. Sometimes it might change. So there might be, just to give a few interpretations, you might have a function that is going to model certain bodily functions when x could be the amount of sugar in your blood, right? So you say, okay, things will function this way if the amount of sugar in your blood is somewhere in this range. But if you get too much sugar in your blood or too low sugar in your blood, something else might happen, right? So you have all these ranges. This is the normal range for blood sugar. This is what might happen if it's too high. This is what might happen if it's too low. All the definitions won't be the same because your body's going to do different reactions. Or you can have something modeling the price of a stock or something, right? So as long as the price is within a certain range, this is how we expect the market to behave. But if the price gets too low, everyone freaks out and starts selling shares, or something happens and everyone starts buying shares. You expect something else chaotic to happen based on past events, right? So sometimes what a function does will depend on where you are. So that's why we have piecewise functions, right? So we want to be able to look at a function with different definitions based on different regions in space. And here I think I asked you guys to evaluate some points. So that's a function evaluated at this point. F of 0.5, F of 0.4, F of 2, F of 20. I didn't do this, but just for fun, graph it. What is f of 0.5? F of 0.5 would be 1. How do we know it's 1?
Because it's the same 0.
Okay, so this here, that 0.5 is your x value. Notice that a half is not greater than 1. It's actually between 0 and 1. So the definition I take for the function is the top one, which is just a constant function 1. It's always going to be 1. Once your x is between that. So that's just 1. What about f of 3 over 4? Still just 1. 3/4 is between 0 and 1, so I take this definition of the function, and it's just 1. What about f of 2? What's that? Right, you use the definition, the x plus 1 definition. 2 is your x value. 2 is not between 0 and 1, so you ignore this line. Go to the other line. 2 is actually greater than 1, so we're going to take this function, and I'm going to plug in x equals 2. That gives us 3. F of 20, same idea. 20 is not between 0 and 1. It's actually greater than 1, so I'm going to use this definition, and I'm going to plug in 20. 21 is that. All right. What would the graph look like here? What does the function 1 look like? Let me actually do that. For piecewise function, kind of the newbie instructions. I mean, when you get more experience, you won't necessarily have to do this. What are the parts? We don't need 3 combined brackets. Check endpoints to see where functions, where parts of the function starts or stops. So for example, if I'm looking at this function, notice that there are 2 definitions I have to worry about. There's one that's just the function y equals 1, right? That's the top definition. What does y equals 1 look like? Straight horizontal line passing through the y value 1. Now, do I want all of that? No, I only want the parts between 0 and 1, right? So I draw the whole thing, realize where I want, and then I cut off the parts I don't need. So I'm going to ignore this part of the function, ignore that part of the function. So really this guy is only, it's like that. Then I look at the other one, which is y equals x plus 1. What does that look like? It's linear. Positive slope. Y-intercept is 1, so that it would look like that. Now, do I want the whole thing? No, I only want the part when my x is greater than 1. So I'm going to find 1, and I know I want to be greater than, so there's an open circle, and it goes that way. I ignore this part. So now this part here should look like that. And now what you do for the total graph, you're going to put these on the same picture. And as I said, if you're not sure where this, here's this circle hovering in space, if you're not exactly sure where it should be, just plug it, check the endpoints by plugging into your function. So all I have to do is plug in x equals 1 into x plus 1, and I'd realize that the value is 2. Right? So I know that this circle should be at over 2 over 1 comma 2. And this endpoint would be at 1 comma 1. This would happen at 1 comma 2. That's just relatively where the position should be. So then I can graph the total graph afterwards. So that means if I have to graph f of this equals 1 x plus 1, the picture is going to look like this. So as long as we're between 0 and 1, this is what my function is doing. If I jump into this region, the function is going to freak out and start moving down. Let's move on to domains. When you think of domains, you kind of want to think of where the function works. And by the where, I'm talking about the inputs, the range of x's, right? So basically domain equals set of possible inputs. The set of x values that you can plug into this function and it makes sense, right? That's what I mean by possible. Range is a set of corresponding outputs. This means when you evaluate the function at those possible inputs, the y values that you get, those form what we call the range. Domains may be given by restrictions or dictated by the function itself. So there are times when I can give you a function and I can tell you where I want it to work. I say, here's your function and I only want you to consider this when x is between this value and that value. And then there's sometimes I'll give you a function and I won't say anything, but it should be clear that it can't work everywhere. There are some values that you would not be able to plug in even if you wanted to. So that's what I mean by restrictions. It could be a given restriction or the function itself dictates an answer. So for example, with a restriction, I can say f of x equals 2x plus 1, and then what we'd write is a comma, and I can say something like x between 1 and 3. So this here would be considered the domain. Technically 2x plus 1 would work for any x value I want to plug in, right? But I don't want you to consider for any x value. I give you a restriction. Only take this definition here. So as far as you're concerned, those are the possible things you want to plug into this function. That's your domain. There are other times when the function itself, so if I just give you f of x equals 1 over x, and I don't tell you any restriction, the function itself will impose a restriction on you, because we know that we cannot divide by 0, so our x cannot take on the value 0. So here we can figure out that our domain is the set minus infinity to 0, not including 0, and then 0 to infinity. Right? And that's not something you'd be given, that's something you should be able to look at the function and tell. So let's talk about some common functions.
I have a question.
Yes.
So if there's no restriction, we can assume that the domain is going to be negative infinity to 0 union. Is that right? Or?
If there's no restriction, it depends on what this function looks like. So it can be anything, which is, I'm going to talk about that right now.
All right.
Common functions and domains. There are functions that show up all the time, especially in this class. One class of function is called the polynomial. Polynomial is any function that has this form. your a's are constants, and your n is greater than or equal to 0, and are integers. So basically non-negative integers. So anything that looks like that is called a polynomial. That's the form of a polynomial. Notice that there are plus signs separating terms, and addition is commutative, so it doesn't matter what order I put it in. Right? I can rearrange these terms if I want, but once you can arrange them to look like that, you get a polynomial. So example, x squared plus 3x plus 7 is a polynomial, or 2 minus 5x to the 17 is a polynomial, or pi plus radical 2x cubed is a polynomial, right? Or 7x to the 4th minus 2x squared plus 3x minus radical 7 is also a polynomial, right? Notice that here, these are coefficients. This is like an a, an a, an a, but my x's can only take on powers that are whole numbers, and they're positives or 0. So this x has a power 4, that has a power 2, this has a power 1. If you don't see an x, it really has a power 0, but you don't write it, right? Because anything raised to 0, that's non-zero, you get 1. So these are all examples of polynomials. They're non-examples. These are not polynomials. So for example, y is equal to x to the half plus x plus 1. It's not a polynomial because this is a half power. It's not a whole number. Or y is equal to 2 plus x squared plus x to the minus 1. It's not a polynomial because of this guy, the power is negative. Polynomials cannot have negative power. Or I can have y equals 2 to the x. That is not a polynomial because your x needs to be on the bottom and the power needs to be a constant. So any guy that looks like this, you call them a polynomial. Now, domain of polynomials. Is negative infinity to positive infinity. Polynomials are very nice functions. They work anywhere on the real line. I can literally plug in any real number into these x's, and I will get an answer that makes sense. Right? So this is one class of function, polynomials. The domain, unless I give you a restriction, is everything. It will work everywhere, all the time. Very nice functions, polynomials. 2. Let's look at what we call rational functions. Fractions are called rational numbers, so when you say rational functions, we're thinking of functions that are fractions. In particular, they have this form, p of x over q of x, such that q of x is non-zero. P and q are polynomials. So if I take two things that look like this and I divide them, I create what we call a rational function. The domain of a rational function, assuming I don't give you any other restriction, is all real x, such that q of x is not 0. For q of x, I'm talking about the denominator. the denominator being non-zero is a very important condition. It will work even if, technically speaking, you don't have a rational function. For example, this, according to our definition, is not a rational function because x to the half is not a polynomial. However, that denominator still cannot be zero. You can never divide by zero no matter what. So if you have a polynomial and I don't give you a restriction, the domain is everything. If you have a rational function, I don't give you a restriction, the domain will be any x that makes the denominator non-zero. We'll do examples soon, so don't worry if you don't remember how do I figure it out? I'm going to remind you. Right now, we're just doing definitions. Another class of functions that we will see very often, radicals. Let's look at the basic form first. This is something like y equals the nth root of x. Right, so for example, the square root of x, or the cube root of x, or the seventh root of x. A more general form would be y equals the nth root of some other function that's under this thing. Let's talk about the domain. What is the domain of the nth root of x?
X greater than equal greater than 0.
Nope. I'll give you a hint. What about the cube root of x? Can I plug in negatives into that function? I can. Right? I could take the cube root of -1, for example. What does that mean? That's the number that when I multiply it by itself 3 times, I get -1. That's actually possible. -1 is the answer. -1 times -1 gives me +1 times -1 gives me -1. So it's possible to plug in a negative here. So what's the rule for the domain? Oh, but that doesn't work for this one. The answer is actually piecewise. It depends on what the n is, right? So the domain means x must be greater than or equal to 0, or you can write it as 0 to infinity, and that's if your n is even. Right, so if you have a square root, a fourth root, a sixth root, an eighth root, if the number here is an even number, then what's underneath that radical has to be 0 or bigger. If the number here is an odd number, and it's odd, it actually works everywhere. So it depends on which radical. So this works for all real numbers. That only works when x is 0 or bigger. So if you want to look at the general case, and like I said, we'll do examples of all these. If you look at the domain of something outside the nth root of some random function that's under here, then there are 2 options. If n is even,
That's a 0.
this works for the domain of the original function intersected with the f of x has to be greater than or equal to 0. And it's just the domain of the original function if your n is odd. So those are radicals. There are 2 more common types of functions we will see in this class, exponential functions and logarithmic functions. But I'll talk about the domains of those when we actually start talking about those. Those are in, I think we do that in 1.5 and 1.6. So when we actually get to those topics, I'll talk about the domains of those. For now, let's do some examples. find domains following. A. B. C. D. Let's do this. E. R of x equals 4 over the radical of x plus what is the domain of f?
Zero to infinity.
What?
0 to infinity.
What kind of function is it? It's a polynomial. What's the domain of a polynomial? Negative infinity to positive infinity, or any polynomial. B. Talk about the domain of G. What's the domain of G?
Negative infinity to 0. So negative 2.
Okay, what did you do here? Remember, it's a fraction. Remember, you need that the denominator is non-zero. So you need that x plus 2 cannot be 0. So this means your x cannot be negative 2. So basically on the number line, negative 2, there has to be a hole there. We're fine on this side and we're fine on that side, but there we cannot work. So this means all numbers from negative infinity up to this point, and all numbers from -2 up to that point. So my domain of G is just minus infinity to minus 2, not including minus 2, that's what this parentheses mean. Minus 2 up to infinity. Everything except minus 2 will work. I can plug into this function and I'll get an answer that makes sense. The answer will be a real number on the number line. What's the domain of H? Right, so it's a function, so we have to look at the domains of each part. The top is just a polynomial and the bottom is a polynomial, so on their own they work everywhere. However, because it's a fraction, we have to worry about the denominator not being 0. So here we need x squared minus 9 to not be 0. So what do we have to avoid?
Negative 3.
How did you get that?
X squared equal to 9.
3 squared equals 9.
Okay, so you can say x squared cannot be 9, and then you can take the square root of both sides and get plus or minus radical 9, which is plus or minus 3. Or, if you have x squared minus 9, you can factor. Notice that this is the difference of two squares. So from this you get that x is not 3, or x is not minus 3. So here, either way it could work, but the factoring method is recommended. Because if I gave you something that wasn't a quadratic, or something nice like this that you can move something to the other side, you'd factor is the way you do it. So for most kinds of functions like this that we'd be solving, the idea is to get everything on one side, factor, and then set each factor equal to 0. It's not all the time we'll be able to do this. So yeah, we'd figure out that plus or minus 3 is the guys we want to avoid. So on our number line, minus 3 and positive 3, you have to avoid them. So there are goals here. But I can work anywhere in between. And I can work anywhere on this side or anywhere on that side. So this covers all numbers from negative infinity all the way up to negative 3. I can work between negative 3 and 3. And I can work for anything bigger than 3, from 3 to infinity. So we would write this down as domain of H, negative infinity to negative 3, or 3 to 3, or 3 to infinity. So that's the domain of H. Okay. So what do we need for that to work? So look at each individual. So you look at the top and the bottom separately. The bottom is a polynomial, so itself no restriction. But the top is radical x. What's the restriction there? X must be greater than or equal to 0 for the radical x part. Right. We also need x squared minus 9 to not be 0 because it's in the denominator. Same as the last time, so we know that our x cannot be plus or minus 3. So now how do I actually figure out what the domain of the whole thing is? The trick is to draw each of those on a number line and figure out where the overlap is. So here's my number line. I know for 1, minus 3, and 3, I have to avoid those, but I can work over here, I can work in between them, and I can work anywhere over there. But one other restriction is that I have to be greater than or equal to 0. So here's my 0. So another function, I can be at 0, or I can be bigger. Right? So where does the overlap happen? We're overlapping here, we have to skip 3, and then we both overlap here. Over here, there's only one line, so only one of the functions will work, not both. Here, there are two lines, both functions work in that region. 3 has to be avoided for the second function. So the domain of J is, it starts at 0 to 3. What are the brackets or parentheses? Here?
0 is closed.
Closed, right? You write square brackets to say I can actually choose that value. 0 is a possible value to plug in. So it's included. We use closed brackets to mean included. Number is included. 3 has to be avoided though, because that makes the denominator 0. So parentheses. Number is not included. Or I can be 3 and bigger. Infinity is of course not included, it's not an actual number we can attain. So that would be your answer to the domain here. here. The 4, no problem with 4, it'll work. For the radical, I need my x plus 3.
I didn't hear what it was.
Must be greater than or equal to 0. It's not that serious, you don't have to act serious. Right? Also, and this is the restriction I need for the radical. However, because it's in the denominator, I need my x plus 3 to actually not be 0, because it's in the denominator. So basically what we need is for x plus 3 to be strictly greater than 0, but not equal to it. And so that means my x must be greater than minus 3. So if I'm on a number line, minus 3 is here. I cannot be minus 3, but I can be anything bigger. And how do I write that down?
Minus 3 to infinity.
Yeah. Domain of R is minus 3, open parentheses, because I can't actually be minus 3. To infinity. Any questions? All right, we'll stop there. Hopefully everything I did today you've already seen. That's why we're just kind of just plowing through it. The next 2 or 3 classes are going to sort of be like that. Just remember this, remember this, remember this, remember this. Okay. We'll actually start teaching in chapter 2. I'll point things out as we go along that you might want to look at, but for now we will stop there. I will see you guys next week. Monday. Yes.